So welcome to the Austin Energy Green Building July seminar. Our topic this month is grid interactive efficient buildings. A brief intro to the topic. Grid interactive efficient buildings promise to be a significant new clean and flexible energy resource. They're buildings designed or retrofitted to blend energy efficiency, energy storage, renewable energy, and load flexibility technologies enabled through smart controls to deliver greater affordability, comfort, resiliency, and high performance, both to homes and commercial buildings. And they also provide benefits to the electric grid. Our invited speakers today will introduce and expand on the topic of grid interactive efficient buildings, talk about the drivers for the emergence of this topic, and share commercial and residential case studies. Before we get to the main event, we'll start with a few announcements. And as I speak, you should see some links appearing in the chat window to the various resources. So I'll start with AGB residential rating updates. The residential team is updating the single family and multifamily ratings to incorporate the latest code updates and support the climate equity plan. Public comments are now closed. The residential team is addressing comments, updating the ratings, and will publish new guidebooks in August. Is the current plan. The commercial team has updated the commercial rating with new tools. The primary workbook, which is a series of calculators, and the AGB site selection map are now published and ready to use. You can find both of them in the online rating system. More details and instructions are available on the Speak Up Austin page. It's your last chance to register for the US GBC Central Texas Boat Tour of downtown buildings. See sustainable sights from the water, tool around Lady Bird Lake on giant paddle boards that accommodate up to 8 people. Meet for happy hour before the event or arrive no later than 7 to walk to the dock. That sounds like fun. The AIA Austin Design Excellence Conference is coming up in this August, and registration starts tomorrow. There'll be 2 days of in-person courses and a design expo. And you can earn up to 18 AIA learning units. Check out their website for more information. And again, that link will be in the chat. Call for nominations for the Austin Green Awards is now open. Buildings, sites, and infrastructure in the 5-county Central Texas region are eligible to be nominated. Submit by September 12th and save the date of the event, which is October 25th. Seminar has been submitted for AIA learning units, GBCI CE hours for lead professional, and AICP CM credits. Austin Energy Green Building will provide certificates of completion for self-reporting and report AIA hours for all those that attend the entire webinar. All certificates will be emailed. A follow-up email will be sent in a few days with links to the recorded webinar and other resources. Here are the AIA quality assurance terms and the learning objectives for today's seminar. So as we get started, if you have questions during the presentations, be sure to use the Q&A window throughout, and we'll be monitoring that and address those after the presentations, probably in the Q&A at the end of both presentations. So with that, I'd like to introduce our first speaker. Kevin Carbonnier is a senior technical associate at the New Buildings Institute. He focuses on technical research and data analysis. Kevin specializes in building energy analysis, zero energy market tracking, emerging technologies, building grid interactivity, and life cycle carbon accounting. Kevin holds a PhD in architectural engineering and is a certified energy manager. I've had the good fortune to collaborate with Kevin on some projects that relate closely to today's seminar theme, and I'm thrilled for all of us here on the line today that he's able to join us. Thank you, Kevin, and please take it away.
Thanks for that lovely introduction, Greg. Let me get my screen up here. How's that looking for you all?
Look good.
Okay, great. Well, welcome everybody. I'm going to give you a quick introduction on what is a grid interactive efficient building, or a GEB. Sometimes they're just called grid interactive buildings. There's a little bit of a word soup coming around on these, but essentially, as Greg mentioned, these are buildings that can dynamically adjust their building load profiles in a way that's more helpful to the grid, and you can get a win-win situation with buildings and the grid to reduce costs, reduce carbon, and save on energy. So how do we talk grid interactivity? If this is the first time you're kind of hearing this term, these are two of the main areas and a couple metrics to keep in mind as we go through this seminar. So the first is a grid peak contribution metric. So what this really is asking is how much does your building contribute to rush hour on the grid? And we can kind of think of this as, we're all familiar with rush hour and traffic, especially in Austin. How much energy is my building using in the summer evening when everybody's got their air conditioner on? We're all expected to be using energy, but am I using more energy during that time than others compared to, like my building's average? And so that's just kind of like an idea of how concentrated is my energy use during those problem times. And then the second is demand flexibility. So what can your building do about that grid peak contribution? Am I able to shift when I'm using energy? That could be through things like building controls or energy storage. And so if we follow this kind of traffic example, is like, can I commute, at 8 p.m. instead of 5 p.m. And that way I kind of avoid traffic. There's less congestion on the roads. It's a similar idea for the grid. In that way, we've got lower operational cost and lower carbon. So how does that look? What we're looking at here is a heat map of marginal carbon emissions on the Texas grid. And then this is forecasted out, about 10 years into the future, what we're expecting the carbon to look like. And just a quick intro on what is marginal carbon. This might be the first time you've heard the term. And so marginal carbon, basically think of it as if I turn off the lights in my room, which power plant is going to ramp down to adjust based on that reduction in load? And what's the carbon output of that power plant? And so if I shut down my building and that means some solar panels stop generating, then I'm not really saving any carbon. But if I shut down my building and a coal plant is ramping down and that coal plant is a big emitter, then I'm actually, saving quite a lot of carbon. And so when your coal plant shuts down, that's when you've got things like this black square here that you can see in the summer evenings. And then in the midday, this green band, that's when we have a lot of things like solar. And so there's not a lot of carbon on the grid. So when we're, adding or reducing load, we're typically going to be, reducing output from renewable type sources. And they're not at zero, right? So you can see, we're still at 260 kilograms of CO2 per megawatt hour. But the point of this is to say, when is it best for our buildings to use energy and when is it better for them to avoid using energy? And so ideally what we want is our buildings to use more energy in this green band here in the middle, because that's going to reduce carbon emissions. And that's typically also, you can imagine a very similar heat map for system load. So, that summer evening when it's been 100 degrees in Austin for, weeks on end, that's when we're getting these black squares. And that's when, the grid is having to burn additional resources to keep up with that demand. And so what we're looking at here is a supply stack for ERCOT. And so that's the Texas region. And along the x-axis here is the capacity. So this is how much power can the grid put out? And what's the cost on the y-axis to generate that power? And so when we're not really highly loaded on the grid, you can see we've got things like wind, nuclear, solar is also over here. And those are the cheapest resources to run. So obviously that's what the utilities and the grid is going to run first. But then as we get toward capacity, once we get to that really, that black square when the grid is peaking, that's when we are starting to run things like gas, oil. These are like fast response resources that can meet that last little bit of load that's really putting the stress on the grid. And those tend to be significantly more expensive. You can see this is an order of magnitude or two more expensive than the cheapest resource to run. And it also happens to be the most carbon intensive. And so what we want is our buildings and our grid to work together to keep us closer to the left side of this supply stack by doing things like shifting when your building is using energy. And that, reduces the marginal cost for the utility. If you have a time of use rate or an incentive program for your building, that can bring cost savings to you, the consumer. And so we can see there's an opportunity here for both the buildings and the grid to save on costs and win. So how does that look on an individual building scale? What you're seeing here is a sample daily load profile. So this is one day. We can see, we're kind of ramping up. People are coming home, and maybe this is when, you're going to take a shower, you're going to start cooking, you're going to start using more energy in that evening. And if you're in an electric building, that tends to be a bit higher. That's when your air conditioner is coming on. Maybe you've got an electric heat pump water heater instead of a gas water heater. And so, you get that extra little bit of demand there. But this is also when we've got peak energy costs, peak carbon. This is those dark squares that we saw on the heat map. So what can you do? You can do things like load shifting. And so now this new green line is, well, my smart thermostat's gonna pre-cool my home before I get home, so that I don't have to use as much air conditioning during that peak period in this shaded box here. That's something that, it doesn't really cost you anything. That can be automated, and that can reduce your cost just because I'm not, using as much energy when my time of use rate is high. I can also do things like add solar. Solar is going to reduce your energy use during the middle of the day, but also in the early evening when the grid starts to peak. And so there's that little bit of, the sun's not quite set. We're still getting a little bit of output from the solar, and that's actually highly coincident with when the grid is peaking. And then to take it one step further, you can even add things like batteries or thermal energy storage. So then you can really totally actively manage what your building's load profile looks like. And so I can stay flat when the costs are low, really just completely reduce or even go all the way to zero if I have enough solar and storage during that peak time, and then ramp back up overnight when I'm just going to recharge my batteries, re-cool my home or reheat my home. And so if you can imagine, if all the buildings have this smart control capability, the solar, the storage, then the utility and the building can work together through things like price signals, incentive programs to really actively manage how the overall system looks, stay to the left side of that supply stack so that we're keeping costs down, keeping carbon down, and keeping the grid more resilient overall because we're not having to react to extreme weather events as harshly because we've got all of the buildings acting as a resource rather than just being a consumer. And so here's kind of an overall look at it from before and after. So both, these buildings, we can reduce our total peak. So now we're not hitting quite as high, even if, our total energy use might be the same or even a little bit higher in case of batteries because you've got things like your round trip efficiency losses. But that provides you backup power for your home. That provides a resource for the utility. So overall, we come out ahead. So why do we need grid interactive buildings? We touched upon this a little bit in the introduction, and I did as well in that little explainer. Decarbonization is a big driver. So this is a way to decarbonize our buildings. We can do things like install heat pumps, install heat pump water heaters, plug in more electric vehicles in a way that is beneficial for the building and the grid because we're actively managing when that energy use is occurring. We get resiliency both at the building level, if you have things like batteries for your backup power, and for the grid as a whole, because the grid now has this immense resource to reduce stress on the grid by tapping into these resources, by cooling homes sooner, by charging EVs at a time when we're not stressed, while maintaining, occupant comfort, while making sure people have charges in their vehicles when they need it. And all of those good things. There's cost savings, so we're reducing when we're using energy. We're not using energy when our time of use rate is peaking. The utility is saving by not having to run those expensive peaker plants. And then lastly, in some parts of the country, there's some regulations around this. Some energy codes are requiring smart thermostats. Some building performance standards in New York and in some other places are going to start requiring, or limiting your carbon budget. So when you use energy to reduce your total carbon emissions footprint is actually going to help you meet some of these regulations. And then lastly, there's also some self-imposed regulations. Maybe some companies, some large tech companies, for example, maybe want to use 100% carbon-free electricity. And so if they can use more energy, when the sun is shining, they've got excess solar, then they can more easily meet their self-imposed regulations or climate goals. So that's a quick introduction. If you have questions about all that, put them in the Q&A and I'll be sure to get to them later on. But I'm going to shift here to some case studies so you can kind of see how some of these buildings are doing this in action. So the first one here is an educational facility in Vermont, and their main strategy that they did in this building was this 2,000-gallon thermal energy storage tank. And so this is tied into their HVAC system. They have a heat pump chiller in this building, and actually having that thermal energy storage tank improved the building's, the HVAC's performance by getting more favorable energy exchange temperatures in a really cold climate in Vermont. But additionally, it lets them, turn off their chiller when they have enough storage in the tank so that they can avoid using energy, again, when emissions are high or when costs are high. And so what does that look like? They got 7% energy savings across the whole building, not just the HVAC system, 8% emission savings. This number being higher than the energy savings means that they are saving energy when emissions were relatively higher. And they got 2 to 3 hours of HVAC load shift. So what that means is, I have a peak window from, let's say, my time of use rate from the utility is 6 to 9 p.m. is much more expensive than the off-peak window. And so I can just not run my chiller during those 2 or 3 hours. That reduces maybe 20, 30% of my building load during that time, and that's extra money that's going into the building owner's pocket. So on a day-to-day, what does that look like? We have the blue line is the baseline operations, and then the orange line is when you're operating with the thermal storage. And so you can see here in the summer and August, the thermal storage line is a little bit higher overnight because that's when they're charging. So the chiller is running a little extra to load up that thermal energy storage. And then in the morning and in the evening, you can see we've got this significant reduction in demand compared to the baseline to reduce costs or reduce energy use when there's high emissions, which was the primary focus for this particular building, was to reduce emissions. So there was a morning peak and an evening peak that they were deploying their thermal energy storage system to reduce demand during those times. Next is a resiliency spotlight. So this is a GSA General Services Administration. This is a U.S. federal building in Oklahoma City. What they deployed here was massive solar, as you can see here on the roof, paired with battery storage. So this was a retrofit for an office building. They just completed this last year. This was part of a multi-building retrofit operation that they put together. And so, like I mentioned, they did a 300 kilowatt solar array, really large battery energy storage, 500 kilowatt hours. But on top of that, they also did some building retrofits to get some efficiency while they were in there doing this project. So they upgraded their building automation system, or BAS. They did some lighting and HVAC control upgrades, and they upgraded the transformer as well to meet that electrical capacity. And so what happened there, bundling the different buildings and the measures together actually ended up making it more cost effective to do that project. That's not something that's new. If you're going to go in and change your lights, you might as well go in and do some other work while you have limited operations, while you have your contractor engaged. But the battery energy storage system, or BESS, that provided resiliency benefits. You can't really put a number on it. In some cases, if you're a factory that's generating product, you can kind of quantify that in terms of sales or output. But how many how do you quantify the dollar value of having power when the grid is out and being comfortable in your home? So those things aren't showing up on the dollars here, but that's, a very real benefit that the occupants have in this building. And what we see here is that the annual cost savings primarily came from the solar and the battery. Even if the battery, like I mentioned earlier, there's an efficiency penalty of charging and discharging it. So they came out about neutral on emissions, but by reducing their demand charges, because as we know, demand charges in commercial buildings can drive most of the cost, they were able to get pretty significant cost savings just by shaving off those peaks. Okay, and then a third case study here. This is looking at just controls. So there's no energy storage, there's no batteries in this one. This is just what if we could deploy our systems more efficiently in a smart way that kind of looks at what's happening on the grid, what does our time of use rate look like, how can we coordinate our different rooftop units in this school in California. And what they did here is they used what's called model predictive control, or MPC. And so this has basically a software running that updates every 5 minutes. It looks at what's the different temperatures in the different classrooms, and it's basically doing an energy model that's updating all the time for the school. And so that way they can say, okay, look, the time of use rate is about to go up in an hour. If I cool these two different school classrooms, I know what how much of that cooling energy is going to come into this third classroom. So maybe I don't need to run the rooftop unit for that third classroom, and I know it's going to stay comfortable because my model is actually predicting what the indoor air temperature is going to be like in those different classrooms. And the big benefit here is that instead of running all 6 rooftop units at the same time, you can stagger when each of them is used so that you can limit your peak demand. And so how does that look here? They can reduce the peak power by 24% by just not having every unit run at the same time, because if you deploy them in a smart way, you actually can stay just as comfortable without running all of those concurrently, which can drive peaks, which can drive peak demand. And so what they did here as well is they shifted 16% of their cooling from the on-peak period, that's in the time of use rate, to a low price period. And so they saved on costs here as well, while actually being more comfortable than from the traditional controls, again, because they can predict what the indoor air temperature is going to be like over time, which you can't do with a typical traditional thermostat. And you can read more about this and the other case studies. There's links at the bottom of these slides here, and you'll get the slides after the presentation as well. And then the last one here is taking us back to Austin. So this is an ongoing project that NBI is working on with Austin Energy. And what we're trying to do here is quantify the load flexibility potential from things like smart thermostats and water heater controllers. And so this is looking at different affordable multifamily installations across Austin. What we're going to do is go in and provide them with smart thermostats and water heater controllers, so that we can see, quantify, like I mentioned, the load flexibility potential. We're going to do some sub-metering at their panels to really actually measure what's that load drop when the smart thermostat is pre-cooling and then not running the air conditioning maybe for an hour or so during a peak window. And then similar for the water heater, which is something I didn't really talk about in the other case studies, is your water heater is cycling on and off to maintain a temperature set point in the tank. As long as you get hot water, you don't really care, at least I personally don't really care, when my water heater is cycling on and off. And so if my water heater can preheat a little bit and then, not heat the water during an hour or two, as long as I have hot water, it's totally invisible to me. And so if we could just deploy retrofit controls on all the water heaters, then that actually adds up to quite a large, virtual battery, so to speak. And so we want to quantify that so that, if Austin Energy can deploy these across, just about every electric water heater in Austin, maybe that's a way that occupants don't even notice, and the utility gets this huge resource to deploy some load flexibility that, again, isn't going to bother any occupants. And so this study here is, convention, we're going to go and deploy this ideally across 1,000 or more individual multifamily units to quantify, the potential for load flexibility there. Okay, so that's it for the case studies. As I mentioned, there's some links to talk, to get some more information on those, or I'm happy to answer some questions. I know that was kind of a high-level overview of all of those. So in summary, what can buildings do? I talked about a bunch of different strategies here. One thing I didn't really touch upon was just energy efficiency. We can't forget about energy efficiency because, that's just across the board going to reduce your costs, your energy use, and your carbon footprint. And some of those energy efficiency strategies save energy more during when the grid is peaking. Things like, having a better envelope, having better windows. That means I don't need to use my air conditioning as much, and air conditioning is a big driver of peak, particularly in hot climates like Texas. You can enhance your demand flexibility. So again, that's what can you do about your building contributing to that rush hour. You can have end-use controls. So we talked about smart thermostats, having water heaters. Some smart appliances as well can do this. So maybe my clothes dryer or my clothes washer can delay for an hour if it's during a peak. I just throw it in there, and then I kind of let the controls, the smart controls, take care of that on their own. Things like thermal energy storage can also shift your loads. So there's a lot of ways to get demand flexibility from different end uses in your building. You can sign up for demand response programs, so check with your utility. Maybe there's some incentives available if you can shift your load or reduce your energy demand during certain peak windows. And then lastly, you can have distributed energy resources at your building. That's things like batteries, that's smart EV chargers, that's solar PV with smart inverters, like I mentioned before. So depending on, what perspective you're coming from to this seminar, we'll talk about what architects and engineers and owners can do. So for architects, you can design for resiliency and grid readiness. Think about your orientation and massing. Having south and west facing shading can reduce your heat gain and therefore your energy demand during those peak times in hot climates, like I mentioned. Make sure you've got a solar ready roof. Make sure you've got the space, the structural capacity, and all of that. Leave some space for batteries. These things need ventilation. They take up space. Make sure you've got some physical room for that if the building wants to install that in the future. Have space for EV charging. Cooler green roof can also reduce demand during those peak times. And then most importantly, coordinate with your engineers, the utility, your control vendors, because all of this requires smart controls, which, as we know, if we don't think about that intentionally and make sure everybody's on board, it's not going to work if the controls aren't in place. And so maybe we'll hear about that from the other speakers later on. What can engineers do? Design and specify grid interactive equipment. So things like having your heat pump water heaters meet these grid interactivity protocols, which are now out. Things like OpenADR. ADR is automated demand response. CTA 2045. These are just different standards that you can check that the equipment is compliant with, so that the utility or third-party aggregator can communicate with that equipment to implement some of this load shifting. But again, energy efficiency first. Don't forget about energy efficiency. And also, coordinate with the architects. You're getting the idea here. Everybody needs to coordinate together. What can owners and operators do? So automate everything. The more that an individual person, and anytime you have to have a human in the loop, that's going to reduce your uptake. That's, I'm not going to be bothered sometimes to go and, adjust the thermostat controls. Make that automated, sign up in a utility demand response program. The more you can automate it, the more you don't have to think about it. As long as, I'm getting hot water and I'm comfortable, then, I kind of think, let the equipment do what it's going to do, and then I'll just get some cost savings out of it. So get grid connected equipment, things like smart thermostats, heat pump water heaters, and batteries. There's some others as well, but this is not an exhaustive list. Make sure it all responds automatically. and educate and engage occupants, particularly in commercial buildings. Make sure everybody knows that this is a peak time, so that might be why the lights are dimming a little bit. Hopefully they're just not even noticing, but that might help kind of smooth things over if, you know, it's a half a degree or a degree warmer and I'm not sure why. If people understand why something's happening, then they're more likely to, you know, be okay with it or be on board. But again, always have overrides. So this is for engineers, architects, everybody. You know, if anytime you're going to introduce something that could bring an inconvenience, make sure there's an override. If that outlet's off because it's peak period, make sure there's a way to flip it back on. And then lastly here, there's this grid optimal LEED credit. So this is an alternate compliance pathway for the grid harmonization credit. If you're designing a building, this is one way to do some demand flexibility. There's a tool and a calculator in there to kind of put in your load shape and see how you're scoring on these different metrics. There's some design guidance fact sheets available on the Grid Optimal webpage, and there'll be a link on the next slide there. So we've got different fact sheets based on building type. What's the top 5 things you can do for grid interactivity in those buildings? And then regionally as well. So we have one for Texas and the Southern Great Plains. So depending on what your grid is like, what your climate is like, what are some top 5 things you can do to enhance demand flexibility? So as I mentioned, all of those are on the Grid Optimal webpage. Here's the link. And then there's also an ASHRAE guide that's going to be coming out. I think they've actually changed the name recently, so I need to update this. But this is basically a design and operation guide for grid interactive buildings, which will be a resource available coming in September, October. So thanks for your time and attention. Again, please put any questions in the Q&A, and I'll be happy to answer those later on. Back to you, Greg, or whomever's running the show.
Thanks, Kevin. That was really great. And then I know a few of you have already put some questions in the Q&A, so keep those coming and we will get to those at the end. We'll transition over to our next speakers. They're working, speaking in tandem. The first they're going to be giving a case study information about a project here in Austin in which they're implementing some of these technologies. First, I'll introduce Cass Brewer. He's the president of Ledgestone Development Group, a parent company of Legacy DCS, Legacy Multi-Home Construction Services, and Brewer Design Solutions. He's responsible for leading a highly passionate and competitive real estate team with decades of experience in residential, resort, and multifamily development. Cass has a vision to create and build companies that elevate customers' lifestyles, embrace the environments in which they're developed, and reduce the impact to the planet by creating sustainable and energy efficient designs. He'll give a brief introduction to the project and a little bit about Legacy and why they're doing this pilot. And then secondly, Brandon Rickett. He currently serves as the business development manager for both IES Texas Solar and IES Energy Solutions. With over 10 years of experience working for IES in various roles and capacities, ranging from small-scale residential sales to large-scale commercial project development across the state of Texas, Brandon uses his vast experience with scopes ranging from the deployment of roof-mounted solar modules, ballasted racking systems, electrical power distribution, DC wiring, startup, testing, and commissioning to lead the custom development of solar solutions for some of the largest companies in many different verticals. Currently, Brandon helps lead new business development efforts across multiple sales channels and has been a part of over 1,500 solar installations in the Central Texas area. He has a BBA in marketing from UT San Antonio, and he's part of the team that did the actual install for the project we're about to learn about at the ADI. Cass, let me share your slide. And take it away.
There you go. Thank you, Patricia. Nicely done, Kevin. Thank you all. Yeah, excited to be here today. This is, you know, just looking back at the history of working with Austin Energy Green Builder Program. I think we did our first project in the mid 90s, working with Austin Housing Finance Corp and doing affordable multifamily housing. So I've had experience working with the program for a long time, and you really champion the program and enjoyed following it along. We opened our doors in 2008, focused on differentiating ourselves with building highly energy efficient homes. So we started out with single family homes, but really graduated into focusing on developments that can really encompass everything from site orientation, how we're utilizing rainwater collection, and just optimizing the site to really have a forward-thinking approach to building, using Austin Energy Green Building principles and others learned along the way. It was interesting with listening to Kevin's presentation. It starts early when we look, at a raw piece of land and try to figure out what we're going to do, if it's, more attached product or broken up in single family and things of that nature, just depending on a lot of the things we do are in infill type locations. So you're constrained with land, which is, gets a higher yield of homes, to be able to pay for a higher cost of land. So we build communities, architecturally themed, and lifestyle forward approach. With the energy focus is really our main differentiator, we think, as you go through positioning of the homes, orienting good roof orientations for solar arrays, and then understanding construction science of how you put the envelope together and what type of windows and insulation, and using 2x6 walls and very high quality windows, HVAC equipment and all that with LED lighting and those things. As we've graduated over the years, keeping up with evolving technology, we're excited about the future and the goals of this program. And we like to push ourselves, further and, challenge our education and ultimately wind up with buyers that are overwhelmed with their homes. A lot of people don't come to us as like, I want, the most highly green built home there. We kind of force it on them. And the feedback afterwards has been incredible. The best home I've ever lived in. I can't believe my energy bills. Everything's so quiet. Those sorts of things. That lifestyle element, or how you live in your home and the health of your home. The feedback we get has been phenomenal. We've done now completed 4 big or developments, if you will, that have been with Austin Energy, the reserve at Lake Travis. Out on, these are outside of the city of Austin, so it shows our alignment with the program. Westside Landing, which was in Lakeway, as the first net zero capable community in Lakeway. Did Isabella in South Austin, and just recently finishing up the Addy off of Capitol Texas Highway. Why we went this way, I think some of it was really pushed with the recent challenges that we've had with our energy grid. And, other than sticking a generator out there and say, okay, I'm going to bypass an outage with, a generator. I'm like, how can we think differently and be able to run this house without support of the grid at all? And so that, it takes experts like Kevin and Brandon, who you'll hear from later, and other associates that we work with to kind of really get together and put our heads together and think about how we can do that in a semi-affordable way. I mean, it's not, this is not inexpensive equipment and things of that matter, but being smart about it and in our approach and what is kind of optimizes the spend versus return on value through savings and your impact you're putting into the environment. So we took it on a project at the ADI with, a full battery backup and solar array combined with a smart energy system by SPAN, which is invented by some of the groups of Tesla that broke off and created this smart panel, which is really optimizes energy use. And I'm excited for Brandon to talk a little bit more about it. But that was really like, I got to use this. I went to we stay engaged with product evolution and things of that nature. Usually the best place to do that is through some of the energy green building conferences and the National Home Builders Association, a conference in Las Vegas. This was recently, but seeing the products that are out there, helping us push us faster to a zero demand home living. So that was like, we came back from that conference with that panel, like we got to use this, and then worked with IES and Brandon to combine the batteries and the solar to really give us a pretty fantastic product. This, if you wouldn't know. Any of those features are really in the house unless you see them in the garage, but you feel them. You feel them in your electric bills, and you got the comfort of if there's an outage that you're covered and you can run your home comfortably, and refrigeration and air conditioning and things of that nature through any event. So we're excited to be part of the program today, and appreciate the invite, Patricia, to talk more about this, and happy to answer questions after we get into it. So I know, Brandon, if you want to kind of get more into the nuts and bolts of the system.
Yes, sir. All right, let me get my presentation. Okay, so here we have, as Cass alluded to, the ADI project that we recently completed off Capitol Texas Highway. You already heard the introduction that Pat gave. I work at IES. I've been here for almost 12 years now. I've kind of helped start the solar division within IES as a company. We're a nationally recognized electrical contractor. We've been in business since 1973, doing electrical contracting work, and solar was something that we got into in early 2010 when it was becoming more popular for people to look at incorporating solar, retrofitting existing homes, new construction. And so we've been leading the development for IES here within Texas for residential and commercial, working with Legacy DCS in their home building process and incorporating some of the features that we're going to learn about today. All of their houses within the ADI community are pre-wired and prepped for solar, with conduits running from the roof all the way to the equipment wall. We have a handful of projects that are getting solar integrated as part of the design of the system. And we've got one additional battery system that's going in as well, that's going to be grid interactive. So here's kind of the project overview. We wanted to provide enough storage power to run the entire home, and also incorporate the smart technology that Cass mentioned earlier with the SPAN panel. And we'll get into a little bit about how the SPAN panel works with all the circuits of the house, working in tandem with the solar and also with the battery system. This is just kind of a project overview. We've got backup and emergency power becoming increasingly popular. We've all kind of lived through the last seasons of winter, from Snowmageddon to the ice storm and everything else in between. Just having an alternative energy source of backup power is pretty critical for today, especially with the grid resiliency and grid demand and all the peak demand information that was shared earlier. Austin Energy started to allow for backup systems to be installed in their service areas. Whether you have solar or not, you can get a battery system included as part of your home's electrical. So with these things in mind, we move forward with the AIA number 3. This was developed. It was focusing on the concept of electrical island resiliency as a measure against power outages. So basically during an outage, you've got the ability to run your solar system, your batteries, and also all the circuits inside your house. You're kind of on an island, if you will, separate from the utility. With this system, we have 16 solar panels mounted on the roof. We've got 3 IQ10 battery systems in the garage. We've got a IQ controller, which is essentially a transfer switch. And then we also have the span panel. So some of the objectives of this project were to be able to specify what circuits are going to be on backup during an outage. With the span panel, you actually can pick and choose what you want during an outage to come on immediately. And so that's kind of one of the big benefits of having an immediate source of power by way of battery systems, and also the span. You can pre-program settings to where only certain things come on during an outage. So you're extending your battery's capacity. You're not running things that aren't critical for your home's existence, and you're able to extend the outage period. We wanted to create a system with the concept of electrical islanding in order to reduce the electrical load, thus reducing the required size of the battery storage system through efficient mechanical equipment. These solutions, we've got a 4.64 kW AC system comprised of 5.76 kilowatt DC of solar panels to provide 50% of the annual energy required by the home. Like I mentioned, we've got 3 batteries that are in the garage, configured for whole house backup, so we can run every circuit inside the house. We've got the span panel, which actually replaced the main service panel, which gives the owners direct control over the circuits during an outage. So if you're going through an outage and your dryer's off or your oven's off and you want to turn it on, the span will allow you to do that and kind of give you an insight as to how long you can run that device based on your current storage percentage. We've got a PV system integrated into the backup system to maintain battery microgrid with solar during an outage. So when an outage happens, the PV system, if it's during the day, will remain on. It'll keep the batteries charged. It'll feed the house directly to keep the power high, so that if we're in the middle of summer, you can run the air conditioning unit. You can obviously run your refrigerator and lights and plugs and everything else. Reliability and energy independence. So solution to power loss during unreliable grid conditions and outages. The system's projected to produce 9,095 kilowatt hours in its first year. Cost benefits, grid-tied solar power system designed to reduce electric costs. So the system's obviously grid-tied, so it's connected to the utility grid, and it's going to augment any of the energy consumption that the building requires directly from solar. $965 saved during the first year of operation. Passive envelope features plus efficient mechanical equipment included to reduce electrical load, thus reducing the required size of the battery storage system. So this is a span panel. This is just a stock image of it. It's a smart home panel. It has the same breakers that you would use in a normal traditional panel, except it's basically like a computer. The way that the breaker system works is you've got an app on your phone where you can turn on, turn off certain things during normal grid operation. If you start to see that there's a device in your house that's using more power than you'd like it to be, you can set program settings on when to turn that device on, when to turn that device off. You've got full capability of managing and controlling all the circuits during an outage. Like I'd mentioned earlier, you can have pre-programmed settings for the items that you want critical that do not turn off even during an outage. And then as you determine if this is more of an extended outage or if this is just a small blip in time, you can turn on the circuits that you would like, everything from lighting to plugs to large appliances. Everything can be controlled from the app, and it works in tandem with the battery equipment. So it can kind of give you more information as far as how much capacity you have and how long, based on the current time that you're using, the amount of power from the batteries, how long you can go with the current outage. Some of the expected outcomes that we had with the system, 9,095 kilowatt hours, 5.76 kW PV system. These are just kind of a summary items of what the system is going to generate. The building's usage, the offset percentage, the positive environmental impacts. This is all speaking towards the carbon reduction, everything that speaks towards the battery system and the solar panels, and what kind of environmental impact the system will have over its 25-year life cycle. So as a company, IES, we have an in-house engineering firm that does all of our drafting and design work, that everything gets permitted through City of Austin, Austin Energy. We have to illustrate how we're going to incorporate this technology as part of the building's electrical system and also with the utility electrical system. So the AIA 3 project was engineered with several goals in mind. The solar powered system designed for the AIA is designed to be able to turn the home into an effective electrical island during a power outage. So this is by way of the IQ controller. It has an MID built in so that when it senses that the grid is down, the transfer switch immediately transfers power from the batteries to the house. It's milliseconds of time. You won't even see your clocks reset on your microwave or your oven. Design a solar powered system that provides reliable and sustainable energy while cutting electric costs over the next 25 years. So we use this 25 years. This is kind of what the manufacturers are warranting the equipment to produce power. But obviously, even after 25 years, there's still going to be an operation. This is just what the warranty of the system comes with. The design method of the system, the PV system was wired through a combiner box to consolidate the interconnection equipment, streamline the IQ microinverter disconnect, and into the same IQ system controller as the PV system. So as part of our process during new construction, we try to get all of the electrical required features of the system to be ran internally. We put a Solodeck box on the roof. We run metal flex conduit through the house. We terminate everything in the garage for the batteries. We run conduits external for safety disconnects, AC disconnects. And so we take everything from a new construction standpoint of where everything's going to get mapped out during construction, and we try and run wire and conduits internally so that everything can be staged during construction. And then when the house gets closer to finishing stage, we can come in and pull wire through those conduits, make all of our connections as the construction project continues. The system is designed to be able to assign specific circuits for the backup system. So we already kind of touched on that. Here's kind of the cost metrics of the system. So we've got a $59,931 was the total cost. We've got a tax credit of $15,582. This tax credit's actually now increased starting this year to 30%. Austin Energy had a rebate program, still have a rebate program for anybody who's looking at doing grid-tied solar. It's directly from Austin Energy. And then we've got a net cost of $41,849. This includes all the panels, the microinverters, batteries, the span panel, all the installation, IQ controller, everything included. Some of the lessons that we learned with the advancement of battery storage technology and using NEC, one of the required items that's necessary is a heat detector. It's just one of the steps that we had missed during construction was using the existing smoke detectors as part of our architecture of design. We could have easily had them add an additional one during construction. We had to add that after the fact per the NEC, something that we had missed. Additionally, the batteries must be 36 inches above garage finished floor. So this lower level battery here, if we thought about it a little bit differently, we could have picked an alternate wall or maybe used it in a different form or fashion so that that lower battery would be more in compliance. So we had to add a bollard to prevent a car from hitting it during a garage. Another thing that kind of came up during our inspection discovery of what is required for these battery systems. So we put a bollard in, and we also put a heat detector in. As part of a new construction project, wireless internet is something that's one of the last steps, if not the last step. And with all of this equipment, through its communication with the IQ controller, with the SPAN device, with the battery systems, it does require an internet source. And so kind of getting more involved with the timing of when wireless internet is going to be available is definitely one of the lessons that we learned, that we can't really commission the system until wireless internet's at the house. So for new construction projects, just having clarity as far as when that wireless internet will be available is a helpful step in commissioning the system. Okay. I'll be here for any questions, or if you want to discuss this project, just feel free to chat in the Q&A.
Thanks, Cass and Brandon, for letting us know about the ADDI project.
Sure.
We are working on a case study to publish this fall about the project. So all of those technical details and some photos and diagrams to show off for those of you that have gotten a piqued interest in knowing more about the project. Greg, do you want to take care of the questions at the beginning that Kevin may not have answered already?
We can start working through the questions. I think a few of them I'm going to paraphrase to talk more generally about topics, because Kevin has been active in the Q&A, answering some specifics directly. First, I want to thank our guest speakers. So this is the start of our Q&A session. We still have time for more questions. So if you have a question that is on your mind or something that comes up during the conversation, please just enter it in the Q&A. I guess the first question I have, something that came in for Kevin, was about a particular AE load shedding rider. But I was wondering, Kevin, if you might talk about the place of utility rate design and program design in the landscape of grid efficient interactive buildings, and maybe what you've seen in other places as this has become more predominant.
Yeah, absolutely. Yes, thank you for the reminder to turn on my camera. So we found that the utility rate structure is the primary, driver and signal for building operators to adjust their behavior. And so time of use rates historically have not really been aligned with reducing energy when the grid is peaking or when carbon is high. We're seeing some improvements there, and there's going to be some more innovations for time of use rates that will change to real time or dynamic pricing, where you'll get actually a 24-hour curve of what's the price going to be for tomorrow for electricity. And that way, if you've got a smart building with things like energy storage, you can plan out what your day is going to look like for charging your battery or charging your thermal energy storage, and really optimizing what your energy bill is going to be for that particular day. That's not really something that exists quite yet, only in some places where they're piloting it. But that's kind of the movement generally that we're seeing, where you're going to get more granular, more dynamic pricing over time, and then ideally things like, even your fridge could optimize the way it's using power to optimize your utility bill. Again, we're not there yet, but that's the primary driver. And, updating those rates from the utility, there's a whole regulatory process, so that's always kind of slow. You can talk more about that from your Austin Energy perspective. But there's definitely a bit of a lag just, from that process of keeping up with the rapidly changing grid and generating landscape, the explosion that we've seen of solar on homes, particularly in places like Hawaii and California, where the carbon landscape is moving faster than the rates can really match. And so if we have things like dynamic rates in the future, where that you can just change that day to day, and then there'll be a signal from the utility that's just kind of ongoing, and then your building automation system or your equipment can just tap into that signal and sketch out what your next 24 hours are going to look like, then that's really the next big step of where everything's going to be automated and optimized to, again, get that win-win for the buildings and the grid.
I wonder, Brandon or Cass, do you have anything to add to that? Pretty thorough response, maybe from what you're seeing on the residential side, and like a desire for those kind of incentives as a driver for putting more of these systems in the residential space.
I mean, just a quick point. So like with time of use net metering or time of use metering systems where, I know it's not real apparent here in Texas, but in other markets where they charge peak demand for times in which you're using more power, these battery systems can help shed a lot of that requirement. There's kind of a fork in the road when it comes to these battery systems. You can save it at 100% full backup so that if you know a storm's coming, or if you know there's going to be a grid outage, then you can be at 100% and kind of ride that outage. But if you're dealing with just normal conditions and there's no threat of an outage, you can set it to where the batteries are going to use self-consumption. So you can actually shed a lot of the building load by distributing that stored energy from the battery system. So I think as we continue to develop the integration between utility demand and these battery storage systems, we can look at deploying energy when reserves are at max, and we're needing some of that stored energy to help deliver. And then in that same vein with time of use, you can also charge the batteries when grid energy is much cheaper as well. So I think utilizing those resources for its strengths and help alleviate some of that peak demand is important.
Great, thank you. So Kevin answered another question already that I think is relevant again to all the panelists. The specific question was about audience member was surprised that he didn't include east shading on a list of what architects can do. Is data showing something less than the significant eastern solar gain that I know in the field? I think feel free to answer that question sort of on the air, Kevin, specifically. But for me, it brings up a larger question is, we were talking a lot about add-on technologies, controls, and sort of the technological side of grid interactive efficient buildings. But the word efficiency is right there in the name. So where does the old-fashioned efficiency and passive design strategies play in to the landscape?
Yeah, so just to quickly answer so we recommended west and south facing shading primarily because that reduces your HVAC loads, during the evening, which again is that kind of rush hour time when the grid is peaking. That's not to say east facing shading isn't beneficial. All energy efficiency and passive solutions in particular are very helpful for just reducing your load overall at all hours, which of course is beneficial. That reduces your utility bills, that reduces the need for the utility to burn fossil fuels to provide that energy. And so those were just some recommendations that give you efficiency during that particular time. But of course, good envelope, good windows, efficient HVAC systems, all of that kind of stuff still applies. Efficiency first is kind of the golden rule across the board for any of these things.
Yeah, a lot of those traditional methods really don't cost a lot more. They're just come in the planning phase. And working with a good architect team and understanding those opportunities, like Kevin's saying, I mean, at the end of all those parts and pieces add up to the whole that really helps drive that energy savings.
Great, thank you. A specific question for Brandon and Cass. If the grid is down for many days, like let's say 10 days, will 3 batteries keep the ADI 3 skeleton crew power running that long? Or if not, like how long can it do that?
Yeah, so like you've got 30 kilowatt hours worth of battery capacity. Something to also remember that I touched on earlier in the presentation, that as long as the sun is out, you're actively producing solar energy in tandem with that battery deployment. So you're delivering energy directly to the home, you're delivering energy directly to the battery system. I mean, obviously, you can't throw a party in the house and just, run every light and every appliance and everything else. But I think for critical circuits to help, keep the home livable, hot water, refrigeration, critical circuits like lighting, you're probably going to want your internet, stuff like that. Those are things that have very little power draw. It's the larger loads of the house that are going to have the larger impact, which is heating and cooling. And so depending on what kind of comfortability you like, and if you have alternative forms of heating, like a fireplace or something of that nature, there's ways that you can extend that battery capacity and extend that time duration. That's kind of the cool thing about the span, and also in tandem with the battery system, is you've got a window into how much capacity you have, how much you're currently using from the batteries. If you make adjustments, it'll tell you how much time you're buying by turning things off. Like if your AC unit is running and it's 115 degrees out, feels like temperature, you'll extend your battery capacity by days by turning that air conditioning unit off. But it's
yeah, I mean, but I think we lost Brandon, but yeah, the cool thing about those batteries, I mean, with augmented by the solar panels, I mean, you can really stretch it out. And, with the technology that's out there, I think it was an earlier question, but I just remembered that you can augment your power in the evenings with the battery storage and utilize that for really staying off the grid. And then your system's also intuitive to know when storm events are coming and things of that nature, to say, okay, we've got a thunderstorm coming. We need to rack up the power in these batteries, to make sure that if there is a power outage, there's capacity. So that's that technology that's automated in the system. It's really cool. And all that's evolving, so quickly. It's fun to watch as the technology moves. But ideally, I mean, you can run the house comfortably and, off the sun. I mean, it's got a car charger in there. I mean, you can charge your car, all that with this home. Using, back to what Brandon was saying, you can't, be crazy. You have it, you're cooking Thanksgiving dinner and you got everything going and all that. That's going to use a little bit more power. But if you're paying attention to what you're using, and being smart, when you're cycling things, I mean, don't charge your car at the same time you're doing laundry and doing all that stuff. Charge your car at 3 o'clock in the morning. Those sorts of things. So you're balancing out the consumption, and you can really stretch it out.
All right, thanks. A couple of technology specific questions have just come in. The first, I guess, for anyone on the panel, are there any residential applications that you've seen for thermal storage, either chilled cistern or water storage tanks, that have been implemented on a smaller scale?
I can start that one. So the short answer is yes, particularly water storage tanks. So, basically, I won't say every, but just about every new heat pump water heater on the market today has CTA 2045 or some grid connectivity. And the water storage in the tank itself is a thermal battery. And then similar for smart thermostats, you might not think of it this way, but the thermal mass of the home or building itself is a thermal battery. If I pre-cool my home, the walls, the slab, all the equipment, all of the stuff in there will cool, store that energy, and release it back into the space. And so your question maybe is getting more towards things like active thermal storage, where maybe you have like integrated thermal storage with your HVAC system, which they are currently piloting some things. I think it's more on the commercial scale. There might be some residential scale things that might be a little more on the fringe. But there are some phase change materials built into rooftop units, for example, that are currently being piloted in some projects that are, coming out of national labs. Some manufacturers are piloting some of that equipment. So I think we'll see some of that in the next probably 5 years or so, where you just drop in a new rooftop unit and it comes in with phase change material that can give you 3 hours of load shift, just all in one package.
Very cool. We have a question about the lifespan of batteries, I guess, when used to store solar energy.
I think it's 10,000 cycles, 10 years is what they're warranted for through the manufacturer.
A question directly for Cass. Are there any plans to install geothermal in future projects, or is that something you've already done?
I have not, and always interested in looking into different technologies. We do a lot of work in the west side of town, so there's a lot of rock. But definitely not afraid of it. Just haven't gone down that road yet.
I think this is phrasing a few different topics that I see in the Q&A, and maybe this is for any of the panelists, and maybe also Pat, who is our one of our resident code experts. What sort of challenges or maybe new opportunities have you seen in energy codes, electrical codes, et cetera, that maybe previously some of these systems were not really defined in code or addressed in code, but maybe codes are evolving to allow and address in a better way now?
I can start a little bit. Currently, we have some code amendments in the Austin Energy Code, City of Austin Energy Code for demand response technologies. And so like on the residential side, having an internet connected thermostat, looking towards having that CTA connectedness in the water heater. That's an exception to the timer requirement for electric water heaters. So there's some items there that we already have. I'm on the 24 IECC residential committee. And so there are a few things coming in through the 24 that are connected to demand response. There's still a lot of the more basic items that Kevin has covered. But there are some readiness requirements that are coming along in the 24. So if you're interested in some of these things like electric vehicles, electric readiness, those are coming into the 24 energy code. So there's a lot of stuff coming, and we have some basic stuff already here.
Right, thanks. I think that sort of takes us to the end of our Q&A. If I missed a question and you would like an answer, please reach out to us and we'll try to get you that answer from the panelists, or if we can answer it, we'll answer it for you as a follow-up. So I'd like to thank our panelists again for sharing great insight and a wonderful discussion. Thanks to all of our attendees. We had great turnout today, really excellent. I am asked to tell you to please take a moment to complete the survey link placed in the chat that you should see now. And finally, to close us out, as a reminder, everyone that registered today will receive a follow-up email with resource links, including a recording of the webinar. All attendees that joined us for the webinar will receive a continuing education certificate for self-reporting GBCI CE hours and AICP CM credits. If you provided your AIA number during registration, we'll report your AIA LU for attending this webinar. You can go to our website in a couple of weeks for information about our September seminar on ratings. Thank you again to the attendees and the panelists. That was really excellent content. Can't thank you enough. And with that, we will sign off.
Glad to be here. Thank you.
Thank you.
Thanks, everyone.